protect yourself and your company from liability in the event of an explosion due to insufficient safety zones, consider the following steps. Firstly, obtain written confirmation from the customer specifying the exact class, division, group, and zone area requirements. This documentation should be signed and dated by an authorized representative of the customer. Secondly, if possible, independently verify the zone area using recognized standards such as NFPA 70, National Electrical Code, or IEC 60079. Consult with experts in explosion safety to ensure the zone area is appropriate for the specific materials and conditions. Thirdly, thoroughly document your analysis and verification process, including any discrepancies between the customer's requests and your findings. Keep records of all communication, calculations, and supporting documentation. Fourthly, if you have concerns about the adequacy of the zone area provided by the customer, communicate these concerns in writing. Recommend appropriate changes or additional safety measures to mitigate risks. Include a disclaimer that you are not responsible for any damages resulting from insufficient safety zones. Fifthly, consult with an attorney to review your contractual obligations and explore potential legal protections. Sixthly, obtain appropriate insurance coverage to protect your company against liability associated with explosions. Seventhly, regularly monitor the adequacy of safety zones and make adjustments as necessary based on changes in materials, processes, or other conditions. By following these steps, you can minimize your company's liability and demonstrate due diligence in providing safe control system designs. However, it's important to note that ultimate responsibility for determining and enforcing appropriate safety zones rests with the facility owner or operator. It is crucial to maintain detailed and accurate records throughout the entire process. This documentation serves as evidence of the steps taken to ensure safety and compliance with relevant standards. Furthermore, it is important to have a clear and well-defined scope of work with the customer. This should outline the responsibilities of each party involved in the project, including the determination and implementation of safety zones. The scope of work should also address any potential limitations or assumptions made during the design process. When verifying the zone area, consider factors such as the volatility of the materials, the presence of ignition sources, and the ventilation in the area. Different materials have different flash points and explosion limits, which will affect the size and classification of the hazardous zone. Ignition sources, such as electrical equipment or open flames, can increase the risk of explosion. Adequate ventilation can help to dissipate flammable vapors and reduce the size of the hazardous zone. In addition to NFPA 70 and IEC 60079, there may be other applicable standards or regulations that should be considered. These may include local building code, fire codes, or industry-specific standards. It is important to be familiar with all relevant requirements and to ensure that the control system design complies with them. When communicating concerns about the adequacy of the zone area, be specific and provide supporting evidence. Explain the potential consequences of an explosion and the reasons why the current zone area is insufficient. Recommend alternative solutions, such as increasing the size of the zone or implementing additional safety measures. When obtaining legal advice, ask the attorney to review the contract with the customer and to assess the potential liability risks. The attorney can also provide guidance on how to mitigate these risks through contractual provisions or insurance coverage. The insurance policy should provide adequate coverage for property damage, bodily injury, and other potential losses resulting from an explosion. It is important to review the policy carefully to ensure that it covers all potential risks and that the coverage limits are sufficient. Continuous monitoring of the safety zones is essential to ensure that they remain effective over time. This may involve regular inspections, testing, or other monitoring activities. Any changes in materials, processes, or other conditions should be evaluated to determine their impact on the safety zones. When making adjustments to the safety zones, be sure to document the changes and to communicate them to all affected parties. This will help to ensure that everyone is aware of the current safety requirements and that they are following the proper procedures. In summary, protecting yourself and your company from liability in explosion-proof control system design requires a multifaceted approach. This includes obtaining written confirmation from the customer, independently verifying the zone area, documenting your findings, providing warnings and recommendations, getting legal advice, considering insurance, and continuously monitoring the safety zones. By following these steps, you can minimize your company's liability and demonstrate due diligence in providing safe control system designs. Always remember to prioritize safety and to consult with experts when necessary. This information is for guidance only and should not be considered legal advice. It is essential to consult with qualified professionals for specific advice related to your situation. Understanding the different classes, divisions, and groups within hazardous location classifications is paramount. Class I locations are those where flammable gases or vapors are or may be present in the air in quantities sufficient to produce explosive or ignitable mixtures. Class Roman II locations are hazardous because of the presence of combustible dust. Class Roman III locations are those where easily ignitable fibers or materials producing combustible flyings are present but not likely to be in suspension in the air in quantities sufficient to produce ignitable mixtures. Within Class I, there are two divisions. Division 1 is a location where ignitable concentrations of flammable gases or vapors exist continuously, intermittently, or periodically under normal operating conditions, or exist frequently because of repair or maintenance operations or because of leakage, or in which breakdown or faulty operation of equipment or processes might release ignitable concentrations of flammable gases or vapors, and might also cause simultaneous failure of electrical equipment. Division 2 is a location where ignitable concentrations of flammable gases or vapors are not likely to exist under normal operating conditions, and in which flammable gases or vapors are handled, processed, or used, but which are normally confined within closed containers or closed systems from which they can escape only in case of accidental rupture or breakdown of such containers or systems, or in case of abnormal operation of equipment, or in which ignitable concentrations of flammable gases or vapors are normally prevented by positive mechanical ventilation, and which might become hazardous through failure or abnormal operation of the ventilating equipment, or that is adjacent to a Class A Division 1 location, and to which ignitable concentrations of flammable gases or vapors might occasionally be communicated unless such communication is prevented by adequate positive pressure ventilation from a source of clean air, and effective safeguards against ventilation failure are provided. For Class Roman II, Division 1 is a location in which combustible dust is in the air under normal operating conditions in quantities sufficient to produce explosive or ignitable mixtures, or where mechanical failure or abnormal operation of machinery or equipment might cause such explosive or ignitable mixtures to be produced, and might also provide a source of ignition through simultaneous failure of protective equipment, or where combustible dust of an electrically conductive nature may be present. Division 2 is a location in which combustible dust is not normally in the air in quantities sufficient to produce explosive or ignitable mixtures, and dust accumulations are normally insufficient to interfere with the normal operation of electrical equipment or other apparatus, but combustible dust may be in suspension in the air as a result of infrequent malfunctioning of handling or processing equipment, or where combustible dust accumulations on, in, or in the vicinity of electrical equipment may be sufficient to interfere with the safe dissipation of heat from electrical equipment, or where combustible dust is in the vicinity of electrical equipment and is likely to be ignited by abnormal operation or failure of electrical equipment. Within each class and division, gases and dusts are further categorized into groups based on their ignition temperature and explosion pressure. These groups are typically labeled A, B, C, D for gases and E, F, G for dusts. Specific equipment is then designed and certified for use in specific groups. The NEC, National Electrical Code, Article 500 and following articles, provides detailed guidance on the requirements for electrical equipment and wiring in hazardous locations. IEC 60079 is a series of international standards covering electrical equipment for explosive atmospheres. These standards provide requirements for the design, testing, and marking of equipment intended for use in hazardous locations. Understanding the equipment protection levels EPL defined in IEC standards is also critical. Equipment is categorized as EPL GAR, GB, or GC for gas atmospheres and DAR, DB, or DC for dust atmospheres, with gondor representing the highest level of protection. When designing control systems for hazardous locations, several protection methods can be employed. These include explosion-proof enclosures, intrinsic safety, purging and pressurization, and non-incentive equipment. Explosion-proof enclosures are designed to contain an internal explosion and prevent it from propagating to the surrounding atmosphere. These enclosures are typically made of heavy-duty materials and have flame-tight joints. Intrinsic safety is a protection technique that limits the electrical and thermal energy in the circuit to a level below that required to ignite a flammable atmosphere. Intrinsically safe circuits are designed to be incapable of causing ignition, even under fault conditions. Purging and pressurization involves maintaining a positive pressure of clean air or inert gas within an enclosure to prevent the ingress of flammable gases or dusts. This method requires a reliable source of clean air or inert gas and a control system to monitor the pressure. Non-incentive equipment is designed to not produce sparks or hot surfaces capable of igniting a flammable atmosphere under normal operating conditions. The selection of the appropriate protection method depends on the specific application and the characteristics of the hazardous location. Factors to consider include the class, division, and group of the hazardous location, the type of equipment being used, and the operating conditions. Proper grounding and bonding are essential for electrical safety in hazardous locations. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock. Bonding connects all metal parts of the electrical system together to create a low-impedance path for fault current. All equipment used in hazardous locations must be properly labeled and certified for the specific class, division, and group. The label should indicate the equipment's protection method, temperature rating, and other relevant information. Installation of equipment in hazardous locations must be performed by qualified personnel in accordance with the NEC, IEC standards, and other applicable code and regulations. Proper installation is critical to ensure that the equipment functions as intended and provides the necessary level of protection. Regular inspection and maintenance of equipment in hazardous locations is essential to ensure that it remains in good working condition. Inspections should be performed by qualified personnel and should include a visual examination of the equipment, as well as testing of its electrical and mechanical functions. Maintenance should be performed in accordance with the manufacturer's recommendations and should include cleaning, lubrication, and replacement of worn or damaged parts. It is important to have a written hazardous area classification plan that clearly defines the boundaries of each hazardous location and the specific hazards that are present. This plan should be based on a thorough risk assessment and should be reviewed and updated regularly. Training is essential for all personnel who work in or around hazardous locations. Training should cover the hazards of flammable gases and dust, the requirements for electrical equipment and wiring in hazardous locations, and the proper procedures for working safely in these areas. Emergency procedures should be developed and implemented to address potential incidents in hazardous locations, such as explosions or fires. These procedures should include evacuation plans, fire suppression strategies, and medical response protocols. Compliance with relevant codes and standards is essential for ensuring safety in hazardous locations. The NEC and IEC standards provide detailed requirements for electrical equipment and wiring, and other codes and standards may also apply. It is important to be familiar with all relevant requirements and to ensure that the control system design complies with them. A thorough risk assessment should be performed to identify potential hazards and to evaluate the likelihood and severity of potential incidents. A risk assessment should be used to develop appropriate safety measures and to prioritize safety improvements. A management of change process should be implemented to ensure that any changes to the control system or the facility are properly evaluated for their impact on safety. This process should include a review of the potential hazards, the adequacy of the safety measures, and the training of personnel. A safety culture should be fostered throughout the organization to promote a commitment to safety at all levels. This includes providing employees with the resources and training they need to work safely, encouraging them to report potential hazards, and recognizing and rewarding safe behavior. Furthermore, it's crucial to understand the concept of temperature classification, often referred to as T codes, which indicates the maximum surface temperature that the equipment will not exceed. This is important to ensure that the equipment's surface temperature remains below the ignition temperature of the surrounding flammable substance. Common T codes include tone T2, T3, T4, T5, and 6, with tone having the highest temperature rating and 6 the lowest. When selecting equipment, the T code must be appropriate for the specific gas or dust present in the hazardous location. The overall control system design should incorporate redundancy and fail-safe mechanisms to minimize the risk of system failures that could lead to an explosion. For example, critical sensors and actuators should have redundant backups, and the system should be designed to shut down automatically in the event of a detected fault. Proper cable selection and installation are critical to maintaining the integrity of the control system in hazardous locations. Cables must be rated for the specific environment and must be installed in accordance with the NEC, IEC standards and other applicable codes and regulations. Cable glands and fittings must also be appropriate for the hazardous location and must provide a secure and flame-tight seal. Surge protection devices should be used to protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. Surge protection devices should be installed at the point of entry of power and communication cables into the hazardous location. Human-machine interfaces HMI used in hazardous locations must be designed to be safe and reliable. HMI should be located outside of the hazardous area whenever possible. If the HMI must be located within the hazardous area, it must be certified for use in the specific class, division, and group. Consider the use of wireless communication technologies in hazardous locations. Wireless devices can reduce the amount of wiring required and can improve flexibility and mobility. However, wireless devices must be carefully selected and installed to ensure that they do not create a spark hazard. Also consider cybersecurity. Control systems in hazardous locations are vulnerable to cyber attacks that could compromise safety. Implement appropriate cybersecurity measures to protect the control system from unauthorized access and malicious software. These measures should include firewalls, intrusion detection systems, and regular security audits. Perform regular functional safety assessments to verify that the control system is functioning as intended and that it meets the required safety integrity level SIL. Functional safety assessment should be performed by qualified personnel and should include a review of the system design, testing of the system functions, and an analysis of the potential failure modes. Regularly audit your safety management system to identify areas for improvement. Safety audits should be performed by qualified personnel and should include a review of the safety policies, procedures, and practices. It is important to remember that safety is an ongoing process, not a one-time event. Continuously monitor your safety performance, identify areas for improvement, and implement changes to enhance safety. Stay up to date on the latest codes, standards, and best practices for hazardous locations. These are constantly evolving, and it is important to stay informed to ensure that your control system design is safe and compliant. Seek out training and professional development opportunities to enhance your knowledge and skills in hazardous locations safety. There are many resources available to help you stay up to date and improve your expertise. Network with other professionals in the field to share knowledge and best practices. Learning from others can help you to identify potential hazards and to develop more effective safety measures. Actively participate in industry organizations and committees that are involved in developing codes, standards, and best practices for hazardous locations. This is a great way to stay informed and to contribute to the advancement of safety in the industry. By following these guidelines, you can help to ensure that your control system design is safe, compliant, and reliable.